Yes, thank you. So on the road towards higher precision, I think one will reach a point where it's not sufficient to analyze observed signals, but one may need to understand the physical origin of why things are changing. And this is a progress report and some efforts in this. We're trying to understand the physical origin of the jittering of velocity in the sun. And the principles then to try to assemble the spectrum from as basic principles as are practical. And in this particular case, we start with the non-magnetic surface granulation, which is responsible for most of the flux coming from the sun. We model the solar surface with three-dimensional hydrodynamic models. We use these models to compute spectra, and there are two models of the sun that are used here. The first one, we compute the complete spectrum. Complete means more than 500,000 spectral lines, basically everything from Vault to these databases. We get a complex spectrum, and this has the advantage of being able to study, blended lines, things from the ultraviolet to the infrared. The other model, we compute only one single spectral line, an idealized line, but this permits one to study what happens if you make small changes in the strength of the line, in the excitation potential, or something similar. The way one obtains lines from spectra from these 3D models is you can use a fully spatially resolved situation as here to the left. You get a huge number of line profiles from rising granules, sinking intergranular lanes and whatnot. Or you can average everything over time and space and you get what is at the right. You get the synthetic line profiles and the bisectors changing from differently strong lines. Is that what we're doing? No, it is not. What we're doing is that make the spatial average over a few thousand points in the simulation area, but we keep it temporally resolved, or rather we sample 20 time instances, 20 snapshots during the simulation sequences. And these are selected such that they are independent or appear to be independent. There are different structures of the granulation at each of these times. This just shows one example. What happens, we have here one from the full spectrum, one particular, iron line, zoomed up to the right, line disk center and integrated sunlight. And you show the lines look basically like the final ones, except that they are jittering in wavelength. Or we do this from the idealized case, where we have a case to the left, lines of a certain excitation potential, but different strength. To the right, lines of the same strength, but different excitation potentials. And for all these lines, we fit what parameters. We determine what is the width of the line, what is the depth of the line, what is the wavelength position of the line. And we do this for strong lines, for weak lines, for neutral lines, ionized lines, etc. And follow them throughout the simulation. What one finds over the simulation area that is, of course, small, 6,000 kilometers square, there's a jittering of roughly 300 meters a second. If we scale this to the full solar disk, we get roughly 2 meters per second. We have to divide this by a factor of like 150 or 200. One finds that most lines, they vary in phase, but the amplitudes are, have something to tell. So to find what is to be studied, we have to zoom into the details of the synthetic spectrum. And of course, the lines or total number of lines is huge. So one has to find some area, some place where there are lines that are interesting and can be systematically studied. And here is one such region. This is at 525 nanometers, and we have a group of iron lines that are here marked with the letters A, B, and C for the strong lines, the medium strength lines, B, and the weak lines, C. And for such type of lines, now jumping to the idealized lines, we can study the behavior of the wavelength jittering. On the horizontal, on the x-axis, we have here the absolute convective or absolute blue shift, or the shift of the lines. So take, in this case, for a weak line. So if you look, for example, at minus 500, it means that this line was blue shifted 500, and you go up on the plot, and you will find the line that is dashed and that are solid. And these are for lines of different strength. For the dashed line, maybe it's the shift is maybe 450 meters. For the solid line is maybe minus 400 meters. This just shows that for the stronger lines, the convective blue shift is smaller. But these are statistical measures. And what happens at in the averaging towards the statistical average is it contains information because things don't average on the same way. And there are differential line shifts. Here we now have on the horizontal axis the instantaneous line shift between a strong line and a medium strong line, lines that are not very different on the horizontal or the x-axis, compared to what is the shift in lines that are strong and weak, a larger difference in line strength. And if you will see that there is a change such that lines with a greater difference in strength, they also have more jittering. They go more back and forth along the axis. And this jittering is different in different groups of lines. Up to the left here, we have ionized iron 2 lines in the blue. Up to the right, we have neutral iron lines in the green. Bottom left, we have the smallest dependence for lines, iron 1 lines in the red. And we can ask, what is the origin of this? Can this be understood? Yes, this is a plot that shows the run of temperature with optical depth. Optical depth on the horizontal axis, it's not geometrical depth, it's optical depth. And each of the curves shows the realization of temperature in one particular spot on a 3D model. The main point here is that these curves, they converge at optical depth unity. The reason they do so, no matter whether it's a granule or intergranular lane, is because the opacity in the atmosphere increases very rapidly with temperature. And therefore, where the line of sight basically hits a wall, rough there, no matter whether it's granule or intergranular, it will be different on a geometric scale. That is where the weak lines are formed. The strong lines are formed higher up. And there is more variability there. The density is lower. There is no such constraint on what the lines can do. So there's a reason why the strong lines have a greater amount of jittering than the weak ones. So to test such models experimentally is perhaps not trivial because the jittering amplitude for the integrated sun is roughly 2 meters a second. And this differential jittering is maybe 1/10 of that. But we can do this in a spatially resolved mode also, jittering across a solar disk. And this shows the root mean square amplitude of jittering from the disk center at the left toward the limb at the right. And there are different curves for differently strong lines and lines of different excitation potential. And this can be studied with a suitable instrument that has the good time resolution and has a good wavelength stability. And in particular, I think I want to highlight the project that is headed by Nuno Santos in Porto, the POET Paranal Solar Espresso Telescope, a solar telescope that is to be erected on and connected to Espresso at the ISO Paranal, and which will have not only integrated sunlight, but also a certain spatial resolution of the sun, and they should be able to test this sort of theoretical predictions. And of course, assuming these predictions are correct, you could apply a filter for a different amount of jittering in different lines that will in principle, compensate for those parameters. So this brings us to the observational point here. And the main point here is that EPRV spectrometers enable also extreme precision stellar spectroscopy, assuming that the photometry is good enough. And we're now asking how small photometric variations can we follow? And in particular, can we identify activity indices that are distinct from the calcium H and K indices? Calcium H and K, of course, is fine, but it's a chromospheric emission index. And that is it's not in chromospheric lines that exoplanetary radial velocities are looked at. So we're using generously available data from HARPS North. We are selected 1,000 low noise spectra from HARPS North. These are taken at the smallest air masses when a few hours around noon in the summer months on La Palma, The sun is almost a zenith, marked here in red. I mean, atop is the air mass for these years of observations. And these we're studying for various selected line features. For example, here, iron lines at around 525 nanometers, selected lines of a similar character, normalizing their fluxes against a nearby continuum or pseudo-continuum of some kind, and doing this for different types of lines. For example, here are iron lines in the blue. There are iron 2 lines in some region. There are lines in the red. And we measure these fluxes and we follow them for these 3 seasons, 2016, 2017, 2018. And the variations can be identified and they are systematic. And here we show those for iron lines. These are fluxes in these intervals as a function in the left column as function of the calcium H and K index. And this was during a time when activity decreased. So that is marked in the red or dark, which is at the right, when the activity was the highest, the calcium K index was the highest, and then again from 2016 to 2017 to 2018. And these different indices that show the greatest difference is in ionized iron 2 lines. Then we have iron in the blue, in the green, and at the bottom in the red. The right-hand column shows them as versus solar apparent radial velocity, and the correlation is not quite as good. And that indicates that these measures more closely correlate with the activity index rather than the velocity as such. The amplitudes here are small. We're talking about some part in 1,000. It's much smaller than the variations of several percent that we have in calcium H and K. But the main point is that these are photospheric indices. They are more closely connecting to what is measured in the radial velocities. And we have analogous behavior in other lines. Here are magnesium, the green and magnesium triplet, which is sort of beginning to be a chromospheric line, strong lines, and there are other limitations. A question here, of course, how small variations can one follow? As far as the photon statistics alone is concerned, one could search for parts in 1 in 10,000. Now we cannot do this, it seems. There is noise. We don't know where the scattering in the previous plots came from. Is it solar or is it instrumental? This shows the level of scattering in the reference continua, where there are epochs of apparent noise, which simply is not, we cannot use. Another limit comes from tellurics. Here is at the bottom is the amount of water vapor above Roca de los Muchachos, and it correlates with the strength of the sodium D lines. And of course, in principle, you could somehow compensate for the tellurics, but if you want to do this on a level of 1 part in 10,000, it becomes quite complicated. Now, the background of this image or this video, it shows the real solar face, the face of the sun. But the face of the sun, of course, is something like a Janus face. It has 2 sides. One is the one for those who want to study the sun, and the other side is maybe the evil one that is providing the noise. So thank you for listening.
All right, we're over time, so I'm gonna have Marina take your slides away from you and set up the next one. But in the intermediate time while that is happening, if there is a question someone wants to ask, do so. All right, I've got one coming in the middle here.
Hello, thank you for the talk. In your iron and magnesium lines, when you measure the flux changes, is it only in the core that you look at it, or do you also study the wings of those lines?
Sorry, could you repeat? There's an echo here.
Yeah, in the iron and magnesium lines that you were showing in the flux changes, is it only in the core of those lines that you measure that, or also in the wings or other parts?
So the question is about the iron lines we're selecting for this.
For Harps North, and you were showing the flux change versus the S index, calcium index. Was it a flux change just in the core of the line?
Oh, okay. if I understand the question, whether the core of the line or other parts are being, well, what is being fitted is something that is fitting both the line as a whole. It's sort of a pseudo Gaussian function. So we do not make a separate fit to the core or the wings. And one reason is there simply are not data enough. We have 20 points in this simulation sequence, and it would in principle be nice to look at, I mean, the bisectors in different parts. This is not being done, but we are searching or checking things like the width of the line, the depth, the instantaneous intensity, and so on. So this is the displacement of the line as a whole, and that is not sensitive to exact type of fitting because the displacements are much greater than the possible differences in various fitting algorithms.
All right, let's go ahead and thank the speaker.